Let me give you a brief introduction about the speaker. Dr. Chandramani Singh is currently an assistant professor with the Department of Electronic System Engineering at Indian Institute of Science, Bengaluru. He received the ME and PhD degrees in the Electrical Communication Engineering from the Indian Institute of Science, Bengaluru, India in 2005 and 2012, respectively. He was at postdoctoral research with TREC, a joint research team between INRIA, Recruitment Court, and ENSD Paris, from 2012 to 2013, and with the Coordinated Science Laboratory, University of Illinois at Urbana-Champaign, USA from 2013 to 2014. His interests are in the areas of communication network, data centers, information-centric networking, federated learning, etc. Over to you, sir.
Okay, morning everyone. I'm Chandramani Singh. Thanks for the introduction. I'll speak about access management in wireless networks. Right? This access management is also known by some other terminology, says medium access control or resource allocation. Though as we see, resource allocation is more general. Here we will talk of a particular type of resource, and so access management. During the course of the presentation,
Dr. Chandramani, sorry to interrupt you. Will it be possible to full screen the slide? Yeah.
It's not full screen. Let me see.
Not yet. We are seeing your notes actually, so it's showing side by side.
Oh, I see. Okay. Is it full screen? Let me know.
No, it's showing multiple panel, like current slide and next slide, and probably you have to set the display settings.
Because I don't really need next slide, so
I think you can check in the display settings. Display
on the top.
setting on the top. Yeah, duplicate slideshow like that. Click the duplicate slideshow.
fine.
Yeah. Now you see it.
Yeah. Okay. Fine. Yeah. So yeah, we will talk about access management in wireless networks. And during the course of the talk, please feel free to ask questions as and when you have. Right. So you need not wait until the end of the presentation. So we will talk of two types of wireless networks, and we will see what distinguishes them, namely infrastructure-based networks and ad hoc networks. Examples of infrastructure-based networks are cellular networks and WLAN infrastructure mode. So basically, these are networks where there is one special node that coordinates the transmissions. In case of cellular networks, we call it base station or E node B of late. In case of WLANs, it is access point. Right? There are another type of networks where there is no such special node, and these are called ad hoc networks. Examples of ad hoc networks are wireless sensor networks, Internet of Things. Right? So, but in both these types of networks, there is one shared resource that we want to allocate among the participating nodes, and that is wireless medium. What I mean that there is one medium, and okay, huge pointer. Yeah, there is one medium and it has to be used by all the nodes. All right. So it has to be divided, time shared. Often it's time shared. It has to be time shared by all the nodes. Right? And there is a constraint called interference. Well, interference makes us time share things. What we mean that when say this phone is transmitting or say phone is receiving something from the base station, at the same time, the mobile next to it should not receive, right? Because it will see interference, right? So, the channel has to be time shared because of interference. Okay, so this leads to the problem of access management, right? So only if one node or a subset of nodes should access the medium at any point of time. So let's see more formally what access management problem is. So I'll try to illustrate it by a very simple example. So here I have three transmitter receiver pairs. right? So you see pair 1, pair 2, and pair 3. Rather than calling that TX-RX pair, I can simply say link 1, link 2, link 3. So we have 3 links, and they are placed here such that either I can activate the middle one, or I can activate the bottom and the top ones, right? I cannot activate the 2 that are next to each other because that will lead to interference and none of them will be able to successfully transmit. So this is the interference constraint. Now, how do I represent this interference constraint mathematically, or say more precisely via a graph? This can be represented by a conflict graph, right? So for instance, I'll join any 2 links that cannot transmit simultaneously. So I have connected links 1 and 2, and so I have connected links 2 and 3 also, right? So we get a graph where 1 is connected to 2 and 2 is connected to 3. This graph is what we call conflict graph for the network that we have. In general, conflict graph will have so here is the conflict graph for the network that we had. So in general, a conflict graph will be of the form V, E. Notice that vertices in the conflict graph represent links. So 1, 2, 3 here are actually links, and 2 vertices are connected if the corresponding links interfere with each other. Here is more general conflict graph. So you see we have 7 links, and 1 and 3 are connected, means there cannot be simultaneous transmissions over 1 and 3, whereas there could be simultaneous transmissions over 1 and 7. They are not connected. Okay. So this is how we represent interference constraints in the network. Now, what we mean by schedule? A schedule is nothing but a collection of links that can be activated simultaneously. So 1, 5, 6 constitute a schedule, right? They can be activated simultaneously, right? 1 and 2, they will not constitute a schedule. If we talk in graph theoretic terms, right, this schedule is nothing but what we call an independent set. An independent set is a collection of vertices such that no 2 in that set are connected with each other, right? So a schedule is nothing but an independent set in the conflict graph. Here is one schedule. Well, we can represent this schedule 1, 5, 6 in a different form by ones and zeros as follows. So I'll put 1 for the vertex index that is part of the schedule, and 0 for the vertex at the position of the vertex index that is not part of the schedule. So 1, 5, 6 could alternatively be represented as follows, right? 1, 0, 0, 0, 1, 0, 0, 1, 1. Okay. Now, what is the traffic model that we consider?
There is no 7th node here.
I'm sorry.
So there is no 7th.
So
when there is no 7th node
here,
in.
Yeah. When I say node in a conflict graph, I mean it's a link in the original graph in the network. Okay. Each node in the conflict graph. So when I see a node here, it's a link in the network.
No, I'm saying that in the tuple xt there are only 6 elements.
I see. Okay. Because there are 6. So in tuple xt there are 6 elements because there. Oh, I see. There should be one more. You are right. Yeah, it's so there should have been a 0 towards the end. Yeah. Okay. Any other question? Okay. So there is one assumption that I'll make, at least to begin with, and that I'll assume that all the traffic is single hop traffic. What I mean is that you want to transmit from one node to another node via a link. So it can, right? So basically, yeah, traffic is confined to so basically what we mean that traffic is confined to individual nodes in the conflict graph. So there is, okay, so what I mean that there are packets that have to be transmitted from tail end of one to head end of the one. Similarly, there are packets that have to be transmitted from tail end of 4 to head end of 4. So that is what we mean by single hop traffic. We will generalize it somewhere in the middle of the talk. right? So it's clear what is single hop traffic. So what I mean that if I go here, right? So here by single hop traffic, I mean that there will be traffic from see this node to this node. So this will be source, this will be destination. Similarly, there could be traffic from this tablet to this laptop. Again, it's single hop traffic. There won't be any packets that you want to transmit from this tablet to this laptop, right? Because it has to traverse multiple hops then. We will relax this requirement later, but for now, I assume that all the traffic is between the adjacent nodes, right? And so each traffic has to concern with only one node in the conflict graph. Right? Each flow has to deal with concern with only one node in the conflict graph. So I hope this is clear what I mean by single hop traffic. Right? Packets, moreover, I assume that packets arrive at node I at rate lambda I. What does it mean in terms of original network? Packets that have to be traversed over link I, they arrive at the tail end of link I at rate lambda I. Okay, so this queue is actually at the tail end of node I, of this node I, right? So that is source of link I in the original network, and they come at a rate lambda I. So this lambda I has units of packets per slot or packets per second, right? We will treat it as packets per slot. So there is this notion. So the whole system operates like a slotted system. So it operates in slots, and this is number of packets on an average that are seen at the tail end of link I. Each packet has unit size. Again, it's a normalization. It doesn't play a big role in the analysis that or the algorithms that we follow, right? So this QIT will denote the queue length at the tail end of link I at any time t. So we will simply call it queue length associated with link I. Any question up to this point? So this is an abstraction of the network that we will deal with, that we will analyze, or that we will consider in the forthcoming slides. Any question?
So the objective is to minimize this queue length.
We will come to that. We will come to the objective in a while, right? But is the topology, representation of topology is clear? So I have told three things. How do we represent a topology? What do I mean by a feasible schedule? And what is the traffic model? Now let's see how do queue lengths evolve. It's easy. So I'm focusing on a particular link, right? So QIT is the queue length of the link at time t. Now what will be the queue length at time t plus 1? So the assumption is whenever you activate a link, one packet goes out of, one packet is transmitted from source to destination. So you subtract one packet from the queue. So QIT plus 1 will be QIT minus XIT. Notice that XIT could be 1 or 0. If I schedule link I, it will be 1, right? If QIT is 0, then it cannot go negative, right? So that is the reason why I have a plus here. It's max of QIT minus XIT comma 0, and AIT basically is for new arrival. So average expectation of AIT is lambda I. Now what is the scheduling constraint? Scheduling constraint is two adjacent links. So in this conflict graph should not be activated at the same time. So that is, take any edge in the conflict graph, right? If IJ constitutes an edge in the conflict graph, then XIT and XJT cannot be one simultaneously. In other words, their sum has to be less than or equal to 1. So this is scheduling constraint, and this is how queues evolve. Now, before I tell what our purpose is, let me tell you this notion of capacity region. What is meant by capacity region, right? To understand capacity region, let us look at this conflict graph. So I have two links that are attached like this, right? Just consider that each link is getting one packet per slot. Each link is, right? So 1 and 2 are getting one packet per slot. Now, whatever scheduling algorithms we use, their queues will basically explode, right? Because for some fraction of time, I can serve link 1. For some other fraction, or in some other fraction, In some other slots, I can serve 2, but since they both are getting 1 packet in each slot, their queues are bounded to blow up, are bound to blow up, right? So we cannot support. What do we say? The way we express it as, we say that we cannot support this arrival rate, this pair of arrival rates, right? Or we can also say that there exists no schedule that will stabilize the queues when arrival rates. So what is capacity region? Capacity region is set of arrival rate vectors for which there exists some schedule, right, that renders all the queues stable. So clearly 1 will not be part of the capacity region, right? 1 packet per, on an average 1 packet per second to 1 per slot to 1 and 1 packet per slot to 2. That 1 vector will not be part of the capacity region, right? So in fact, if we look at this network, this particular conflict graph, we can convince ourselves that this will be the capacity region. See, we can have on an average 1 packets per slot to Q1 and no packets to Q2. That can be stabilized because you will schedule, how? You will schedule link 1 all the time. Similarly, if we are at half, that is again on the boundary, it can be stabilized if it's right regularly half, if it's a periodic traffic of say all even slots, in all even slots, Q1 gets packets, in all even slot Q2 gets a packet, that can again be stabilized. Basically, you can schedule link 1 in half the slots and link 2 on an average in half the slots, right? So this is the notion of capacity region clear? It can be shown that capacity region is convex hull of all feasible schedules. So what is mean by convex hull? It is again set of all convex combinations. So script X is set of schedules. Take all convex combination of schedule, right? So this is a convex combination of schedules, right? And so set of all convex combination of schedules, it's convex hull of feasible schedules, turns out to be the capacity region. Is the notion of capacity region clear? So set of arrival rate vectors for which there exists some schedule, some algorithm, some protocol that will make all the queues stable. That set is called capacity region. So that means if there is an arrival rate vector in capacity region, there will be some schedule, some algorithm, some scheduling algorithm that will make the queues stable, right? Now here is an interesting question. Is there one scheduling algorithm that will work for all the arrival rate vectors in the capacity region? See, what did the definition of capacity region say? There should be some scheduling algorithm that should stabilize the queue. So there we have a flexibility. If I get one arrival rate vector, I can pick one scheduling algorithm. If I have another arrival rate vector, I can have another scheduling, right? As long as they stabilize the queues, we are okay. But the question is there one scheduling algorithm that will work for all the rates that are in capacity region? The rates that are not in capacity region, we know by definition there will not be any scheduling algorithm that will work, right? But for those rates that are in capacity region, is there one scheduling algorithm that will suffice? The answer is yes. Such scheduling algorithms exist, and they are called throughput optimal scheduling algorithms. We will see those in it. So those are at the heart of this presentation. Throughput optimal scheduling algorithms. So let's see, why are some scheduling algorithms good and why are some bad? So to see that, I'll demonstrate an example of a not so good and inferior scheduling policy. So here is my conflict graph, 1, 3, 2, 4. There are 4 nodes, right? And they are such that either you can schedule 1 or 2 at a time or 3 and 4 at a time. And let us say this is my scheduling algorithm. Okay, first of all, let's see, this is the traffic pattern. So links 1 and 3 receive 1 packet in each odd slot, and link 2 and 4 receive 1 packet in each even slot. Okay, that is the traffic pattern. The arrival pattern is clearly in capacity. Why? Because on an average, you get 1 packet per slot, and you can basically stabilize the queues by doing a clever scheduling. All right. But here is the scheduling policy that I propose. Prioritize links with smaller indices. That means if link 1 is non-empty, you should give it priority over any other link. If link 2 is non-empty, if 1 and 2 are non-empty, but 3 and 4, okay. If 2, 3 and 4 are non-empty, then you should prioritize 2. So that is the policy. And I'll show that that policy is not a good policy, right? So for instance, 2 packets came to 1 and 3 in slot 1. 1 got priority, so 1 was served. 3 could not be served because 1 was served. Now by the time 2 and 4 got packets. Now 2, 3 and 4 have packets. So according to my policy, I'll prioritize 2. I'll serve 2. 3 and 4 will be starved, and meanwhile they will get other packets, right? Now my policy says that I should prioritize 1. So I'll serve 1, and meanwhile 2 and 4 will get packets, right? Now I'll serve 2. So you see that 3 and 4 never get a chance. 2 and 4 never, 3 and 4, sorry. Links 3 and 4 never receive any service, right? Should have been 3 and 4. So this is not so good scheduling policy. Even though my rates were within the capacity region, this scheduling policy couldn't stabilize the queue. So this says that yes, good scheduling policies are non-trivial and require some effort to come up with. Okay. Now, before I go ahead, we'll talk a little bit about cellular networks, that is infrastructure-based networks. So in these networks, a simplified picture of these networks will be like this. So there is a base station and there are n number of users that are connected to base stations. And here only one link can be activated at a time, the graph, right? So the network acts in such a way that it allows only one link to be activated at a time, right? So what will be the corresponding conflict graph? Can anyone tell what will be the corresponding conflict graph? So notice that in conflict graph, say if n is 7, there will be 7 links, and so there are 7 nodes. In conflict graph, there are 7 nodes. And what are the constraints? Communication constraint. If you activate one link, you cannot activate any other. So what will be conflict graph? It will be a complete graph. I just wanted to draw parallel, right? So in cellular network, the conflict graph is a complete graph, right? So that way it becomes a special case of ad hoc network, it looks. But then there are other complications in cellular network modeling. So here, earlier I said that whenever I activate a link, right, one packet goes through. Okay. So there is no notion of channel state. Again, this is a modeling abstraction. After all, it's a wireless network. Even ad hoc network is a wireless network. So there will be channels in good and bad conditions. But when we model the scheduling problem, we assume that channels are perfect. In cellular domain, we no longer do that, right? So there is a notion of channel state. That means even if I activate link, say link 1, what rate I will get or how many packets I'll be able to flush from the queue, that is not fixed. That depends on state of the channel. So channel can be in state H with probability pi H. And if channel is in state H and I activate link I get a rate RIH. So this is, I can transmit, that means I can transmit RIH packets over the link I per unit slot, right? So in some stage, it is simpler than ad hoc setting, but then there are other uncertainties that they also make it slightly complicated. Right? So just to further clarify the things, here is how queue length will evolve in cellular case. So even if I schedule link I, the queue length will not be subtracted by qi by 1, but rather it will be reduced by RIHT. So if XIT is 1, queues will, right, Q will diminish by RIHT. HT is the channel state at time t, and as I explained earlier, the rate over link I at time t will depend on the channel state at that time. Okay, so it's slightly different from what we had earlier. Now scheduling constraint is I can activate only one of the channels, only one of the links. Sorry, only one of the links, right? Because conflict graph is a complete graph. Okay. So now what is the capacity region? See, earlier I said the capacity region was convex hull of all possible schedules. Now it gets slightly more complicated because of the channel states. So I'll have to do one more convexification. I'll have to convexify over all possible channel states. Right. So here earlier, if you draw a parallels, I had alpha I times xi. Right, xi was either 1 or 0. Now instead of xi, I'll have ri. Those are actual rates. They can be any numbers, right? So alpha I times ri. But this whole thing, this inner summation is for given channel condition h, right? So I also have to write one more convex combination, and that is convexify over all possible channel states. So this notion of capacity region, it turns out to be slightly more involved, though it follows the similar logic. So again, as long as the arrival rate vector is within this set, I know that there exists some algorithm that will stabilize the queues. Now the question is there one algorithm that will work for all arrival rates within the capacity region? So before I go ahead and tell about the good scheduling algorithm, I will just summarize the discussion so far by making a comparison of cellular and ad hoc networks, right? So here is cellular and here is ad hoc. I should have written it other way. The first one is ad hoc, second one is cellular. In cellular, there is notion of random channel states, conflict graphs are complete graphs, and sorry for this goof up. So in cellular, there will be notion of channel states, conflict graphs will be complete graphs, and we don't need a distributed solution per se, because there is one coordinator, so that can do all the calculations if required. I mean, any calculation that is required, and it can pass on the schedule or scheduling decisions to all the nodes, right? So a centralized solution suffices, right? On the other hand, in case of ad hoc networks, there is no notion of channel state. Conflict graphs could be general, and we need distributed solutions, right? In the sense, there is no one node to compute the schedule or make the decision that which link should be active and to pass on to all the nodes. All the nodes should learn on their own whether they should transmit in a slot or not. Okay, so that is one difference, major difference between cellular and ad hoc setup. In ad hoc setup, we need distributed solutions. So before I go ahead, we'll have a pause of a minute, and I'll like to see if there are any questions.
Hello, sir.
Yes.
So you told the cellular is having no channel state. Does that mean?
No. I said that it's. I have written it the other way. It's a book of. So in cellular, there will be random channel states. Conflict graphs are complete graphs, and but centralized solutions suffice. Okay. So this points apply to cellular. In an ad hoc, again, as I said, it's not that in ad hoc wireless networks channels will be perfect. It's not like that, but the way we model, the way we abstract the access management problem, we assume that those channel states are perfect, right? So there is no uncertainty. So in case of ad hoc, there is no notion of channel state. Conflict graphs could be general, but we need distributed solutions. Okay.
And another query, sir. You explained about the conflict graph for the cellular thing. For the cellular, for example, if node user 1 is connected to the cellular base station, so like how the graph is getting complete? Because if
I see. Okay. So this is a simpler model where we are saying that only one node can talk at a time. So if one is talking, 2 to n, or in case 2, 3 to 7 should not be able to talk.
Yes.
Conflict graph should also say the same thing. When will you say the same thing? If I connect 1 to all these, all others, 2, 3, 5, 6, 7.
Okay.
1 and 2 are connected. That says that when 1 is active, 2 should not be active. Similarly, 1 and 5 are connected. That says that when 1 is active, 5 should not be active. Right? So 1 should be connected to remaining 6, all of the remaining 6, right?
Oh,
so
okay.
Logic says that 2 should be connected to all of the remaining 6.
Okay. Okay. Okay.
Right?
Okay.
But the point is, point is only one node. In simple terms, only one link should be active at a time. Right?
Yeah.
Okay.
Yes,
So just to clarify this, what I mean that if in a feasible schedule here, this is a vector of length n, and there will be only one. Meaning will be 0. Right?
Yeah.
Out of all these XITs, only one term will be 1.
Yeah.
All others will be 0.
0. Yeah.
Okay. Any other question on whatever we have seen so far?
Sir, I have a basic question. Like after we form a conflict graph, from that we get the schedule, like the tuples which we formed, like 1, 1, 0, 0, 1. So after getting the conflict graph, we get the schedules, right?
Hello?
So yes, sir, I can hear you now.
Yeah, I thought my internet connectivity had some problem. Can you please complete your question?
Sir, I'm just confused over here. After we get a conflict graph, from that we would form the schedules, right?
Yes.
Okay.
Right. Yeah. So conflict graph tells which schedules are feasible. Now, out of all feasible schedules, which is the best one, right? We need to pick. We need to pick so that I can keep all the queues stable, right? So at each time I'll have to pick a. So sometimes when we say schedule, you mean a sequence. So here by when I say schedule, I'm focusing on a time. Sometimes schedule refers to this entire sequence. So at each time I'll have to come up with a combination of links that I can activate, right? And the sequence of combinations of links is called schedule. Right? That is also how people define schedule. Right? For instance, in case of cellular network, at each time I have to decide which node should transmit or receive. Right? That is the decision problem. That is the problem that I have to look at. Any other question? So up to now, we have seen what is the scheduling problem in ad hoc and cellular networks, and what we mean by schedule, what is capacity region, what is throughput optimal scheduling. Throughput optimal scheduling is one algorithm that will work for all arrival rates. Okay. So now we will go to this scheduling algorithm that is at the center of this whole talk, and it's called maximum wait scheduling. This is a throughput optimal scheduling algorithm. We will come to that later. So this algorithm was proposed in early 90s by two gentlemen, Tassivilas and Ephraimidis, and this is like most looked upon thing, maybe I could say, in communication networks. This paper will have several tens of thousands of citations, and following up their work, there have been hundreds of variants of this scheduling algorithm. We will see a few variants as we go along. Right? So let's see what is maximum wait scheduling. Recall this example. We saw that the scheduling algorithm that prioritizes links with smaller indices, that is an inferior scheduling algorithm. What is a good scheduling algorithm then? So here is what a good scheduling algorithm. At each time, okay, so you give a weight to each of the queues. So here is a conflict graph, 1, 2, 3. There are 3 links, the 3 nodes in the conflict graph. That is, these were the 3 links in the original network. Give a weight to each link, right? Okay, so what is the problem now? In scheduling problem is like at each time you have to come up with an independent set, right? And you have to activate that. At time t, you come up with independent set, activate it. At t+1, you come up with another independent set and you activate it. The question is what independent set should be chosen at each t, right? So we define weight for each queue, and here I assume that weight is simply the Q length. Then I compute the weight of an independent set, right? So that is weight of an independent set is sum of weights of all the constituent nodes. For example, in this graph, there are two independent sets, 1, 3 and 2. Weight of 1, 3 will be sum of weights of 1 and 3, which in turn is sum of Q lengths of 1 and 3, instantaneous Q length. Similarly, weight of independent set 2 is Q length of 2, right? Now, once you have the weights of all the independent sets, simply activate the independent set that has the largest weight. That turns out to be a throughput optimal scheduling algorithm. And this algorithm, as the protocol suggests, it's called maximum weight independent set algorithm, right? In case of, so I said that weight of a node will be Q length of that node. Instead of Q length, I could choose any function of Q length as long as that function is concave and increasing function. Okay. So let's see an illustration of it. So let's see, these are the Q lengths. Now, which independent set has larger weight? 1, 3 or 2? What is the weight of 1, 3? Is sum of weights of 1 and 3.
Yeah.
And Q lengths. What is weight of 1, 3?
5.
Weight of 2?
3.
Okay. So which one will you activate? 1, 3.
1, 3. Yeah.
Activated. And say 2 got a packet, right? These packet arrivals are random, right? We only so now which one has larger weight between 1, 3 and 2?
2.
Right? 2 has weight 4, 1, 3 have weight 3. So you will activate 2. And so on, right? So it's clear what is max weight independent set algorithm.
Sir, another query. So right now, if you can see the 1 and 3 as the same, like 3 and 2.
Okay, then you can pick either of those.
Okay.
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 So formally, this is what we do. At each time t, the xt will be solution to this problem, right? Let's see what is here. What does this say? If x satisfies these constraints, the two constraints that I have written, then x will represent an independent set. Is that clear? If x satisfies these two constraints, then x will represent. So x will have ones only at nodes corresponding to an independent set. And then what about the summation? This will be simply the weight of that independent set. Right? So this maximization problem says that the solution to this maximization problem is basically the set with largest basically the independent set with largest weight. That's exactly what we were looking for. Any question on it?
So this weighted scheduling algorithm does not take the priority into constraint, right?
No. It's a different. So I said that priority based thing is inferior. That is a bad policy.
Okay. So for example, even in this weighted scheduling policy, so some packets which has a time critical application for in order to serve some time critical application, so some packets will have high priority. So at that time, whether this scheduling will perform better. Hello.
Clear that solving this problem will give you the max weight scheduling, right? The solution to this problem will give x, where there will be ones at the nodes that constitute maximum weight independent set. See, I'm choosing my x from the set such that xi plus xj is less than or equal to 1 whenever I and j are connected, right? So any x that will come out of this optimization problem, in that x, no two nodes will be no two adjacent nodes will have ones, or they will be activated, right? So this is what we call max weight scheduling policy. It is throughput optimal in the sense that I mentioned earlier. The problem is it is a centralized algorithm. So I could use it in ad hoc setting as well as in cellular setting. But this by the way, this was for ad hoc setting. For cellular setting, we will see in a few minutes. So this is for ad hoc setting. Now to solve this problem, all this Q-length information should be passed at one node. Some node, say some server. That server will solve this optimization problem, and it will tell the best schedule or best combination of nodes that should be active at that point, right? So it's a centralized algorithm. So it's not basically suitable for ad hoc networks, right? And it's highly complex. You see that this is a binary integer problem. Integer problems are certainly much more complex than linear problems or convex problems, right? So it's a complicated problem, and notice that you have to solve it at the beginning of every slot. So that way it's also quite complex. So we look for alternatives, right? But it serves the primary purpose. We were looking for a throughput optimal algorithm, and this is a throughput optimal algorithm. Let's see what changes in cellular setup. In cellular setup, the problem was simpler in the sense that you had to choose just one link, right? You had to choose just one link that you had to activate. You knew that you could activate only one link or only one node in the config graph at a time, right? Now, the difference with respect to the previous criteria is now this. What you see is the weight of a link. The weight of a link is the following. It is some function of the Q length of that link. It could simply be the Q length of that link times the rate that you can obtain over that link at that point, right? If you activate the link at that point, this is the rate that you would achieve. So you do this product. Earlier, in case of ad hoc setup, this RJHT was it was in fact 1. If I schedule link J, then I knew that I would get one packet through. So instead of RJ, I had 1, and that is why, or say, or I had say XJ, right? That is why I had this f of Q length times X. Now I have f of Q length times R. This R could be any number, right? It is the actual rate that you will get at that point over that link, right? So this is max weight scheduling in cellular context. And here distributiveness is not a requirement, because in cellular it's base station that can do all the computations, though there are issues. What are the issues? These Q lengths are, if you are familiar with layering, TCP/IP layering, for instance, which is the basis of the whole internet, which is underlying the whole internet as of now. So these Q lengths are a phenomena at the application layer, whereas medium access happens somewhere at the data link layer. So this application layer information should be passed to data link layer, so that data link layer can make a decision whether the link should be active or not. This goes against the basic principle of layering, right? That basic principle said that all the layers should work on their own, right? So this does have some issue. It also has another issue. Suppose it is let's look at this picture. So it's a cellular system, but it's uplink. That is, nodes have to transmit to base stations. Then to know that base station, to know which node should be allowed to transmit, this base station will ask for Q lengths from all the nodes in every slot, and then it will compute. Then it will decide which link should be activated. So that is a communication overhead. So even if we ignore the violation of layering principle, there is a communication overhead. Each time this base station should know the Q lengths of all other nodes to decide which node should transmit, right? So there are issues with this also. So we will see how the later enhancement or variants solve these issues. So this is about the basic max weight scheduling. Is this clear? What is max weight scheduling? Any question on it? Do let me know if you think you didn't get anything, right? I will be happy to explain. So the basic principle of max weight scheduling, for each independent set, you will compute its weight, which is nothing but sum of the weights of the constituent nodes, and then you will activate the independent set that has the largest weight.
So this f is chosen by like whom? This function f.
Okay. So as I said, f is some concave increasing function. So for example, f could be a linear function, fx equal to x. That meets the criteria. So I can simply ignore f. I can simply use qjt in it instead of f qjt. That will work. So if I choose I according to that, that will work. Right? What it is saying that take any concave increasing function and it will work. The resulting schedule will stabilize all the Qs. So you have full freedom of choose, like choose any f that is concave increasing. Any question?
Hello, sir.
Yeah.
Can you explain what is this RJHFT?
What is?
RJHFT.
Okay. RJHFT. So here we saw that RJH is packets over link J if channel is in state H. So if you are talking of time T, the channel is in state HT. So what will be the rate achievable over link J? It will be RJHT. In case of ad hoc, the rate will be simply XJ. If I activate that link, I'll get 1 packet through. If I don't activate, I'll get 0 packet through. Right? So there was no H there. But now this RJHT is the number of packets that you can transmit over link J in that slot, in slot T, given that channel is in state HT.
Okay, sir. Yeah.
Okay. Any question? Okay. Let me talk of one variant right away before I go ahead. Okay. So here you can think of this problem as following. Rather than solving this optimization problem, I can think of, okay, I take a candidate schedule Y, I compute its weight. The weight of the schedule will be simply this, right? Instead of Xi, I'll be writing Yi. Then I'll take another schedule, right? Say Y prime, I'll compute its weight. I look at all possible schedules, all possible independent sets, and then I'll see which independent set has the largest weight. I'll activate that. That is max weight algorithm. Here is an alternate. Right now at time T, I'm using a schedule. So in the previous slot, I used the schedule xt minus 1. Now I randomly pick a schedule from all available schedules or from all available independent sets. I will randomly pick one independent set. I'll compute the weight of that independent set, right? I'll compare with the weight of the existing independent set, right? The current independent set. If the new one is larger, has larger weight, I'll use it. Otherwise, I continue to use the previous one. This is a simplification of what we are doing, because what I'm suggesting now, it doesn't involve any optimization. All I'm saying that, okay, at time T, at T minus 1, you are using xt minus 1. Randomly pick one independent set, compute its weight. If the newly chosen independent set Y has larger weight than xt minus 1, use Y. Otherwise, continue to use xt minus 1. This is something that works, right? So this is also throughput optimal. Here is slightly complicated variant. You took, rather than one independent set randomly, you pick two independent sets randomly. Okay, compute their weights. Whichever has larger weight, use that. So you don't need to optimize over all independent sets. Just randomly pick two and see which has larger weight, use that one, right? That also works. And that phenomena is, I mean, rather than picking the best, picking the better of the two randomly chosen thing. This works in many contexts, and this is also referred to as power of two choices. So you'll often hear this term whenever this scheduling or resource optimization comes, power of two choices. This is what we mean. So I readily told you two variants of max-weight scheduling. Here is another variant, and now I'll focus on
one question.
Yeah.
One question. So how do you compute this weight of an independent set? Because
okay, this this thing is weight of independent set I. So I have already picked X such that these constraints are satisfied. So that is, so X represents an independent set. What will be weight of X? This summation. I in V F Q I T X I. That is what we think of independent set.
I mean to say that in an independent set there are multiple nodes which cannot communicate with each other.
Which are not connected in the conflict graph.
So I mean, I mean, how can they know that what is the Q length at other node?
I see. So this Q length information we assume, right? We assume that Q length information of all the links is available.
Okay. At all the nodes.
No, you need it at one point, right? So there is one server, right? That has Q length information of all the nodes. Then that server also knows the network topology. That server also knows the conflict graph. So that server will choose an X, that is an independent set, and that server can compute it. So you need a separate server to do this computation. That is why I said that it's a centralized algorithm and it's not suitable for ad hoc networks, right? Because in ad hoc network, there is no such server.
Sir?
Yeah.
Sir, sometimes in some conflict graphs, just tell me if I'm wrong, it is possible to get more than 2 schedules, right? So among all the schedules, which one is the maximum? That one will allow.
Exactly, right? Almost all the time you will have more than one, right? For instance, here there are, in this conflict graph, there are 2 independent sets, 1, 3 and 2.
Yes, sir.
Isn't it? And so see, if there is only one independent set, then there is no problem to solve.
So no, sir, more than like 2, like if there are 3 or 4 independent.
In this conflict graph, how many independent sets are there? You know, 7. Basically, each independent set has just one node.
Yes, sir.
Right? So you have, so if you have more than one, you have to make a choice.
Okay.
If I go back and see this, right now there are many independent sets possible. 1, 5, 6 is one, 2, 3, 7 is another one, 4, 7 is yet another one, right? 1, 4 is one, right? 2, 3, 6 is one, right? So many independent sets are there and you have to pick one, right?
Yes, sir.
Yeah, that is the problem. That is scheduling problem. Which one to pick?
Okay.
Yeah, so for a while now we'll focus on cellular setting, right? So here I said, okay, again there is a, I'll go here. Instead of Qj, I should have written Wj. So see, what is Qj? Qj is Q length of link J, right? By definition. Many a times, so if there is a queue at link J, by head of the line packet, we mean the packet that is at the front of the queue. For how long that packet has been waiting. If we know that time, instead of Q length, I can use that time. So instead of QJT, I can write WJT. What is WJT? It is wait time of the head of the line packet in the queue of link I, right? WIT is wait time of the head of the line packet in queue of link I, right? So instead of Q lengths, I could use those wait times and I'll get a selection criteria, and that is still throughput optimal. So this is a variant of max wait scheduling that we saw earlier. Sometimes we do not know the current queue length information. Even that is okay. So if we have stale queue length information, that also works. So for instance, imagine this policy also works. So if so t is say a number, an integer greater than 1, and for small t between k capital T and k plus 1 capital T minus 1, that is for all this t slots, I could use the queue length information. Okay, again this should have been capital T, so basically capital KT. So basically I'm saying that you could use the stale queue length information. So basically what I'm saying that you note down the queue length information and you use the same queue length information for next capital T slots, and you decide your schedules. Even that works, right? So delayed or infrequent queue length informations also suffice. Let me know if this is clear. So I'm saying that you record the queue length information at capital K capital T and use the same queue length information between K capital T and K plus 1 capital T minus 1. Right? Here it should be K capital T. Right? And it works. Right? Similarly, at K plus 1 capital T, you will again record queue lengths, and you will lose that queue length information for next capital T slots, that, right? So, and so on. So infrequent queue length informations, if you are getting, even those work. Now let's see another variant. So I mentioned one of the problems of this max wait scheduling was this problem that you had to get frequent queue length information, right, from nodes. It turns out that you don't need queue length information at all. You can do do something clever. So here is what I mean. So suppose QIT is queue length at time t. Now you have computed certain schedule, and this is the new queue length information, new queue length before I add new arrivals. So I have not yet added new arrivals, and this is my queue length, right? After adding new arrivals, this is QIT plus 1. So basically, if you look at the earlier evolution, here the first part I am calling Q bar IT plus 1. Okay, so this is an intermediate thing. Yeah, and then I get this. Now here I maintain another counter WIT. And how is this WIT updated? WIT is updated, it's increased by 1 as long as this Q bar is greater than some number, and that some number is R max. It is chosen as per some criteria, right? If it is smaller than R max, then it is reset to 0. That is what it means, right? WIT plus 1 will be 0. This indicator function is 1 as long as this criteria is satisfied. It's 0 otherwise. So WIT plus 1 will be WIT plus 1 if this criteria is satisfied, and it will be 0 otherwise. Right. Now, how does this help? This means that nodes need to inform the base stations only when their queue lengths go below or above R max. See, if the queue length has gone above R max, this node will inform the base station. From then on, one base station will continue incrementing this WIT, right? And it doesn't seek any information from the station. Once this queue length falls below R max, again this node informs the base station, and the base station will reset this WIT to 0. So now you don't need exact queue length information, and whatever information you need it very infrequently, right? So to compute WIT, it turns out that instead of queue length, I could use that counter W. And even this variant of max wait scheduling is throughput optimal. This reduces communication overhead. This also allows isolation of layers because you don't need exact queue length information of application layer. So is this variant okay? Let me know.
Hello, sir.
Yes.
Sir, can you please tell me like what was Q bar again? I mean in the previous slide.
Okay. So you see here the Q length was QIT, right? And then you served XIT as per the current decision. So QIT, XIT times RIHIT. So before you add these arrivals, whatever the Q length was, that I'll call him Q bar. So that is, if once I add these arrivals, this QIT will be, so Q bar IT plus 1, I'll get QIT. So this is some intermediate number. I mean, this is, so it's like you have a queue. First you remove all from Q length all those that you have served. That thing you call Q bar, and then when you add new arrivals, it becomes your new queue.
Okay, sir. Okay.
Okay. So this is some intermediate thing. This is needed for technical regions. In fact, here, even if I use Q, it works most of the time, but it's needed for some technical region, right? But the important point is to update W. The base station can update W without seeking regular information from the nodes, right? And base station could use W instead of Q, and still this new information will continue to be throughput optimal. Okay. So there is one very important extension that I would like to talk about as far, and this is the last thing as far as max weight goes. Until now, we have said that, so this is network, this is not conflict graph. Until now, we have said that the flows or the packets have to go to adjacent node, right? So a packet that arrives here and it has to go to one of the adjacent nodes. That is what we mean by single hop flows. But right, but in general, the flows could be multi-hop. Suppose this node is getting some packets that it has to send to this node TK. So I'll call it flow TK, or sometimes it's also referred to as flow K, or sometimes it's also referred to as user K. So flow K starts at a node SK and it has to go to TK. So this is an instance of multi-hop network. Now, in this multi-hop network, what will happen? The queues at nodes, right? So queue at node, there will be one queue at node I for each flow that passes through node I. For instance, there will be one queue at node I for this flow K, where it will put together all the packets of flow K, right? Packets that have to start at SK and go to TK. Now, what do you mean by schedule? So by schedule, I mean that whether I use this link IJ for flow K. This decision, so the set of these decisions comprise schedule. For any link, I have to decide whether I'll activate it, and if I activate it, for which flow I'll activate it, right? So that's why I have this indices IJKT. X IJKT equal to 1 means I am activating IJ and I am activating it for flow K. Suppose X IJK prime T is 1, that means I am activating IJ, but I am activating it for K prime, and this condition should be satisfied, right? So I am again in perfect channel setup, right? And this condition should be satisfied. That means I can, if I at all activate this link IJ, I can activate it only for one flow. Now, see what was the principle earlier. I should activate a flow, I should activate a link if the corresponding queue length is high, because I want to control queue lengths. Now what happens when I suppose the queue of flow at node I is high, right? And I activate it. It's true that this queue gets flushed by a packet, but that packet adds to the queue here at J. So if queue here is big, I should activate this link. But if queue here is also big, I should not add to the length of the queue, right? So I should take that also into account. So in other words, what I was telling that earlier, the weight of this link was simply the queue length here at I, right? Because I wanted to give this link more weight when this queue length was large. Now the weight of this link will be queue length here minus queue length here, right? in multi-hop scenario, the weight of a link, the way I compute the weight of a link, it will be weight at the, it will be Q length at the tail end minus Q length at the head node, right? Because I don't want this to be high, right? So if it's high, then this should get less weight. It's like this, the node at the head end, it's putting a pressure in the backward direction on this link. More precisely, if I see here this is how the Q lengths will evolve. So Q length at node I for flow K at time Tk plus 1 will be Q length at time T. And if I serve any packet from this flow, my Q length will reduce. But if I get any packet from some other node for this flow, my Q length will increase also, right? So this is how Q lengths will evolve. And as I mentioned, the weight of a link will be now the Q length at the tail end minus Q length of the head node. And basically, otherwise the logic will remain same. Again, I will activate the links for which the sum of their weights is maximum. But right, this variant of the max weight algorithm that we have now written for multi-hop networks, this is also called back pressure. This is called back pressure algorithm. So this was extension of maximum weight scheduling for multi-hop networks. I see that I have only 5 minutes left, so I'll quickly tell about Q length based CSMA. See, that solves the following problem. So as we saw here in case, and now I'll focus only on ad hoc networks. We saw that in the case of ad hoc networks, to get the optimal schedule, you need to solve this problem. That is, someone should have all these Q lengths at its disposal, and that someone should also know the conflict graph. That is the only way that node or that server could compute the best schedule, right? So it's not a distributed algorithm. Here is a distributed algorithm, and I'll try to, so here is an algorithm, and I'll give an example, then we'll stop. Here is what is done. At time T, we determine xt as follows, the right schedule as follows. First, we choose a decision schedule. Decision schedule is a set of links that are allowed to change their state from the previous slot. I'll tell you what we mean via an example. So empty is set of nodes that are permitted to change their state. Change their state means 1 to 0 or 0 to 1 from the previous slot. Now for each node in this empty, this is what I'll do. First, I'll compute a probability. For okay, so for each node in this set empty, I'll do the following. I'll see if there is a link in its neighborhood that was active in the previous slot. If no link was active in the previous slot, then I'll do the following. If any link was active in its previous slot, then I will not do anything. I'll just I'll not activate this. I'll not activate this particular link, right? This is what I'll do for all the links in empty. The links that are not in empty, I'll not do anything for them, right? I'll keep their state unchanged. Okay, now let us come to this. So if for a node in conflict graph that is in empty, if no node in the conflict graph in its neighborhood or no link in its neighborhood was active in the previous slot, first I will compute a probability, right? This probability will be computed like this. It will be computed like, say you can g of qit by 1 plus g of qit. So g is an increasing function of q length. So you can see that if q lengths become large, this g also becomes large and p becomes almost close to 1. So p increases with q lengths. Similarly, if q lengths decrease, p decreases, right? So when q lengths are large, I compute pit, and then I activate this link with I activate this link with probability pit, and I do not activate with probability 1 minus pit. So what you should see is that if q lengths at a node are large, if q length at a node is large, then pit will be close to 1, and with very high probability I'll activate this link. If q at a node is small, then PIT will be close to 0, and with very high probability I'll not activate it, right? So this is similar in spirit to max-weight algorithm, but now a node can take its call independently. A node can take a call whether it has to be active or not independently by just looking at its own queue length. Here is an illustration. So let's say this is current schedule 1.5. It's a valid schedule. First thing I do is I'll have to come up with a decision schedule. Is there one set of links that are allowed to change their state, right? So for instance, and what is decision schedule? It's just some independent set. So 3 and 6 I picked as decision schedule. This is clearly an independent set. Now let's see. I'll have to take a call for each of these two nodes, 3 and 6. For 3, one of its neighbors was active in the previous lot. So I will not do anything for 3. That is here, right? XIT will be, I will not do anything, means I'll keep it quiet. For 6, none of its neighbors was active in the previous lot, right? So 6 can go to active or inactive. It will go to active with probability 6 and inactive with probability 1 minus P6, where P6 is a function of queue length at 6. So suppose link 6 changed its state. It became active. Then this is the new schedule. Now again, I'll pick in the next slot, again, I'll pick a decision schedule. Suppose my new decision schedule is 147. It is some independent set. Now I'll have to take a decision for each of these. 1 has to take a decision for its own, 4 has to take a decision for its own, and so has to be done by 7, right? So you see 7 finds that both its neighbors are active, so it will remain inactive. 4 also finds that at least one of its neighbors was active, so it will also remain inactive. But 1 sees that none of its neighbors was inactive. Then it can go to either 1 or 0. It will go to 1 with probability P1 and 0 with probability 1 minus P1. P1 again will depend on the queue length of 1. If queue length is large, this P1 will be high, otherwise it will be low, right? It will be close to 0. So we see that nodes are able to take their calls on their own based on their individual queue lengths. It turns out that even this random access algorithm, why you call it random? Because nodes are sort of tossing a coin, right? They are making decision probabilistically. So this kind of algorithm is also throughput optimal. So this addresses the problem that was being posed by max weight for ad hoc networks. Okay, so there are several extensions of Qcsma also. For instance, one could use delayed queue lengths. Then there are certain other generalizations. These are quite interesting algorithms, and so I will stop with one mention that until a few years ago, all these standards, say for instance, all these Wi-Fi standards, in there the scheduling decisions were not based on queue lengths because they were against the principle of layering. But more recent Wi-Fi standards, for instance 802.11ax, BE, etc., they have basically started making scheduling decisions based on queue lengths. To be precise, based on something called buffer status report. So many of these things which were just in theory are now likely to come into practice. Okay, so yeah, there are some other things. For instance, there have been work on combining the two algorithms and so on. So I'll skip those details for lack of time, but I invite any questions that you may have at this point. Sorry, I couldn't cover all that I wanted to. Yeah, but do let me know if you have any question.
Participants can unmute yourself and ask questions.
Go back to the decentralized algorithm.
Sorry?
Can you go back to this decentralized algorithm that you discussed?
Yes. You want to see this?
Yeah, this one. So what is the intuition for this if condition?
Okay, so it's like, yeah, so See, if no link in your neighborhood was active in the previous slot, then even if you become active, you will not violate this independent set constraint, right? That is why only then you have flexibility of going to state 1 or 0. If no link in, if even one link in your neighborhood was active in the previous slot, you don't have flexibility of going to 1, because that node will most likely not change its state. And then if you change your state to 1, then you will be violating this independent set constraint. For instance, let us see here. 6 didn't find anyone in its neighborhood in active state. So it could go to 1, but 3 already had someone that was in active state. So it cannot go to 1, otherwise it will violate the independent set constraint.
So, I mean, this algorithm is also throughput optimal, or?
Yeah, this is throughput optimal, yes. This algorithm is throughput optimal, yes. This has though very bad delay performance, and the later versions have tried to address that problem, but nonetheless, it keeps your queues stable. It don't let them blow up. It doesn't let them blow up. Any question? Any other question?
No.
Hello, sir.
Yes.
Sir, like here, the scheduling algorithm, we are basically taking into consideration the interference of, our neighbor nodes and neighbor nodes. Yeah. So if we also consider the channel state also, like the channel state also can go bad and it can be good. So
we are talking here, right? In case of this distributed algorithm, right? The case of this distributed algorithm, right? See here, I mean, you are talking in the context of Q-length based algorithm, this CSM algorithm, QCSM, right?
Yes, yeah.
Yeah. Here, then this algorithm doesn't work. In fact, we know that this algorithm is not throughput optimal in that scenario. Okay. There is a reason for that, but I think, yeah, it will take time for me to motivate it. But this works only when channels are perfect.
Yes, sir. Yeah. Okay.
Yeah. But as we saw, I mean, from the earlier examples, this distributed solution we needed only in ad hoc setup. In this setup, right? Here, centralized max weight was okay. Here, in this situation, I said that there is no notion of channel state. So that algorithm is perfectly fine for it. Now, in practice, there will be a notion of channel state, right? How do we take care of that then? So there are other ways. For instance, in Wi-Fi, we use something called MCS selection, modulation and coding scheme selection, right? If channel is in bad state, I will lower my MCS, right? And I can still use that channel. So there are ways to handle that problem, but as far as access management goes, we treat the channels to be perfect.
Okay, sir. Okay, clear.
Any other question? See something. Delay critical application. So there is a question, will this algorithm hold good for delay critical algorithm applications too, or is it suboptimal solution? Max weight is optimal solution, both from delay and throughput point of view, right? But max weight is, as we saw, was centralized solution. The QCSMA is not delay optimal. In fact, it gives very poor delay performance, and there have been several updates of it, several versions of it that give better delay performance. Okay, so can we stop if there are no more questions?
Sir, can you refer to some papers, I mean, according to these algorithms?
Sure. Okay. So here I didn't put references, but there are two papers that I would suggest if you want to look into it. One is the paper by, as I said, Tasiulas and Ephraimidis. This is 1992 paper. I think it was in transactions of automatic control, I believe, or Okay, that or maybe in JSAC. So, but it's very popular paper. If you just search for it, right, Tassiulas and Ephremidis, Tassiualas and Ephremidis, Mides, then 1992, right? So you'll get to know about this Maxwell algorithms. As far as QCSMA goes, there are two papers that you can refer to. One paper was by Jiang and Walrand. Just search for QCSMA and you will see there was one paper by Living Jiang and Walrand, and another paper was by Shrikant, R. Shrikant. I think Shrikant and me. Just search for QCSMA, right? So those two papers tell all the basics about these two algorithms. And as I said, there have been thousands of papers, if not more, that talk of extensions of these algorithms. Okay. Yeah, so then I'll stop sharing if there are no more questions. And thank you all for attending.
Thank you very much, Professor.
Okay.
Participants, those who have enrolled for the lab sessions, your session will start by 2. So be there. Thank you all.